All right, in section 5.2, we're going to review a couple topics from geometry that will be very helpful as we move forward in looking at some of our trigonometry. The first is a pretty famous one, which is the Pythagorean theorem. And the Pythagorean theorem, everyone knows, is a squared plus b squared equals c squared. But really, more importantly, what we know about those is a and b are legs of the triangle. So they're the sides that are not across in the right angle. And c has to be the hypotenuse. It's the longest side. It's the side across from the 90-degree angle. So in Pythagoras' theorem, it's the sum of the square of the two legs equals the square of the hypotenuse. And the cool thing about Pythagoras' theorem, there are certain numbers that will work, certain integer numbers that will work in Pythagoras' theorem, and we call those Pythagorean triple. So any numbers, any three numbers where the first number squared plus the second number squared equals the biggest number squared is called a Pythagorean triple. Now, obviously, every set of numbers doesn't follow this, but there are quite a few. So in this first example, it says, show 3, 4, and 5 is a Pythagorean triple. So that would be relatively simple. I would just say, is 3 squared plus 4 squared equal to 5 squared? Well, this is 9 plus 16, which does equal 25. So 3, 4, 5 is a Pythagorean triple. Now, example 2 says, show that the three sides of a triangle are a Pythagorean triple. So we have two sides here, 5 and 12. So we have to see if the third side, using Pythagorean theorem, is it an integer. There's always a way to find the third side, but a lot of them have square roots and things like that. So we want to see, does it actually turn out to be an integer? So if I take 5 squared plus 12 squared equals the hypotenuse squared, that's 25 and 144 equals c squared. 25 and 144 are 169. So the square root of 169, c is 13. So 5, 12, and 13 is also a Pythagorean triple. 3, 4, and 5, and 5, 12, and 13 are probably the two most famous Pythagorean triples. So here's a couple others we can check in a similar fashion. We can see, is 9 squared plus 40 squared equal to 41 squared? Well, if we do 9 squared plus 40 squared, 9 squared is 81, and we add that to 40 squared, we get 1681. And if we take 41 squared, I'm getting 1681. So this would be yes. So 9, 40, and 41 are an example of a Pythagorean triple. Not a very famous one, but one nonetheless. So for B, we'll see, is 10 squared plus 49 squared equal to the biggest number, because the hypotenuse has to be the biggest number. So 49 squared is 2401 plus 10 squared is going to give me 2501. But if I do 50 squared, I get 2500. Those are not equal, so this is not a Pythagorean triple. So there are more numbers that are not Pythagorean triples than actually end up being Pythagorean triples. So if we look at this last example, it just kind of shows find the unknown side lengths and figure out, do they make a Pythagorean triple? So we have 9x and 11. So the question is, which one is the hypotenuse? That's really all that matters, and that would be c here. So if I set up this ratio, or this equation, it's going to be x squared plus 9 squared equals 11 squared. Now that obviously has a solution. The question is that solution an integer solution? So we have x squared plus 81 equals 121. X squared equals 40. So x is going to equal the square root of 40. Now technically it's plus or minus the square root of 40 when you take the square root. But for now, we're just going to assume it is the positive root. But keep that in mind, because there will be a time in this class where that negative root actually is very important. And now I can simplify square root of 40. It's square root of 4, square root of 10. So it is 2 square root of 10. So the other side is 2 square root of 10, which is fine, but the problem is that is not going to be a Pythagorean triple. Just because 2 square root of 10 is not a positive integer. So let's look at number 2 of example 4. So again, first we got to figure out which side is our c, and in this case the 20 is the c. So we have x squared as one of the legs plus 10 squared as one of the legs equals 20 squared as one of the legs. So x squared plus 100 equals 400. So x squared equals 300. So we'll take the square root. So the square root of 300 does not turn out to be nice. So right away we know it's not a triple, not a Pythagorean triple, which is okay. But I can simplify this. This is square root of 100 times square root of 3, which is going to be 10 square root of 3. So Pythagorean theorem will be very important. We deal with a lot of right triangles. And remember, Pythagoras' theorem is only valid for right triangles. Any other triangle, we'll have to use other rules and laws that we'll come up with in the future. The last thing I wanted to kind of go back and look at in this section is what are called special right triangles. There are 2 really important triangles in math and in geometry that have very, very nice ratios of their sides. And trigonometry eventually will have to do with a lot with the ratios of sides of the triangles. So these 2 are the 45-45-90 triangle, which is sometimes referred to as the isosceles right triangle, because it's the only right triangle that has 2 angles that are the same. And the nice thing about this, these have ratios of 1, 1, and square root of 2. Or more importantly, the legs are the same. So sometimes we'll call this x and x, and the hypotenuse is always the leg length times the square root of 2. Now a 30, 60, 90 triangle, not quite as famous, doesn't have quite a name like the isosceles right, but what it is it's half of an equilateral triangle. An equilateral triangle with all 60-degree angles, if I take half of it, then I get a 30, 60, 90 triangle. And the cool thing about this is here, now you have a 30-degree angle across from it. This side is 1. The hypotenuse is double what we call this short side. And then the long side is this short side just times the square root of 3. So if this is x, the hypotenuse is always double that short side. And again, short side always across from the 30. And then the long side is going to be x times the square root of 3. Now, since these ratios are always the same, all we have to do is have one of these sides, and we can pretty much find all the other sides. So let's look at some examples here of how we can find some missing sides in 45, 45, 90 triangles and 30, 60, 90 triangles. So this first one is a 45, 45, 90 triangle because it has a 90-degree angle. This is 45, so the other one, since they have to add to 180, would have to be 45. Now what we know is we know the sides across from a 45 have to be the same. So if the one across from this 45 is 4 root 3, then the one across from the other 45 would also have to be 4 root 3. Now if we look up above to find the hypotenuse is just one of the legs times the square root of 2. So we can do that same thing here. So we take one of the legs and we multiply it by the square root of 2. So 4 square root of 3 times square root of 2 is 4 square root of 6. So this would be y, this would be our hypotenuse. Hypotenuse is always square root of 2 bigger. All right, let's look at example 2. Example 2, we have the hypotenuse, but we're trying to find one of the legs. Now in this case, we know the legs are the same x and x, and here we have 2 square root of 2 for the hypotenuse. But remember from above, that is just the side length, the leg length, times square root of 2. So what number times square root of 2? We get you 2 square root of 2 essentially. So that is going to be just 2. Some people also will write it sometimes the hypotenuse is the square root of 2 times the leg. Well, if I do that, I could get 2 square root of 2 equals square root of 2 times the leg, which was x. Divide by both sides by square root of 2, and there's my same answer of x. So it depends if you just want to kind of think about it or if you want to use a more algebraic technique. So example 3 is talking about a isosceles right triangle again, because these two are the same. So x and y really have to be the same, so x and y are going to be the same. So our hypotenuse is 9. So we know that the hypotenuse is the leg times the square root of 2 equals 9. So this leg, which is x, all we have to do is simply divide both sides by the square root of 2. So x is going to equal 9 divided by the square root of 2. Now that is a fine answer, but if you remember from geometry, most times we don't want to keep radicals in our denominator. So what we'll do is we'll multiply the top and bottom by square root of 2. So 9 times the square root of 2 is 9 root 2. And square root of 2 times square root of 2 is 2. So this is what we call a rationalized denominator, where there are no radicals on the bottom. All right, let's look at example 4. Now 4, 5, and 6 are dealing with the 30, 60, 90 triangle. And remember, we know the hypotenuse is going to be double the short leg. And the short leg, again, the short is always across from the 30. And then the long leg, which is across from the 60, so in this problem it'll be here, is going to be the square root of 3 times the short leg, or short leg times square root of 3. So in this case, we have to see what side we're given. So we're given 2 root 3 across from the 30, so this is the short leg. It's always nice if you have the short leg in a problem like this. So the short leg, the hypotenuse is going to be double that. So if I double 2 root 3, 2 times 2 square root of 3 is 4 square root of 3. And the long leg, the one across from the 60, by our definition, is going to be the short leg, which is 2 square root of 3 times another square root of 3. So this is going to become 2 times 3, because square root of 3 times square root of 3 is square root of 9, which is just 3. So the long leg is 6. So this triangle is in ratio 2, root 3, 4 root 3, and 6. All right, let's look at this example over here. Again, it's a 30, 60, 90 triangle. Because we have the 60, we have the 90, so this has to be the 30. So this is the short leg, but that's not what we're given in this case. We're given the long leg. Now we know the long leg is the short leg times the square root of 3 is the long leg. So in this case, the long leg is 5 square root of 2, and the short leg is x. So we get x times the square root of 3 equals 5 times square root of 2. So what I'll do is I'll divide both sides by the square root of 3. So I get 5 square root of 2 over square root of 3. And again, I can rationalize and get rid of that root in the bottom. So I'll just multiply by root 3 and root 3. So that's going to give me 5 root 6 over 3. That's the short leg. So that's this side right here. Now we still have to find the hypotenuse, which is the longest side across from the 90. But the hypotenuse, remember, the hypotenuse is just double the short leg. So because these ratios always hold, we can just keep using this same thing. So the hypotenuse not wide, is 2 times 5 square root of 6 over 3. So that's going to be 10 square root of 6 over 3 for y. So let's look at a final example with a 30, 60, 90 triangle. We were given the short leg. The second we were given the long leg. This one we're given the hypotenuse. So the hypotenuse is 3. And we want to find the short leg and the long leg. This is 60. This is across from that. So our short leg, remember our hypotenuse is double the short leg. So our hypotenuse is 3 is 2 times b. So b is just 3 over 2. So the short leg is 3 over 2. If you're given the short leg or the hypotenuse, these are actually pretty easy. It's the second example we did with the long leg that is a little trickier. For the second part, we know the long leg is equal to square root of 3 times the short leg. Well, the long leg in this case is we don't know. It's a times square root of 3 times the short leg, which is 3 halves. So just for convention, we typically put the fraction in the radical last. So this would be 3 over 2 root 3, or 3 root 3 over 2. So using these pre-existing ratios of sides in a 45-45-90 triangle and a 30-60-90 triangle, we can get answers to lots of the sides of the triangle. When we move forward, we'll actually see that every angle and every kind of triangle has these special ratios. They're just not quite as set and nice as these are.